How do you make sure that your drone flies where it needs to fly? All the controlled flight is about following a three-dimensional trajectory with high precision. And so, how fast do you need to rotate each rotor to achieve that? Luckily, there are some very powerful control techniques out there that can solve this problem in no time. My name is Mark, and I will teach you exactly that, how to design and apply them to a UAV. In this course, you will first learn about how to mathematically model a UAV drone with 4 propellers. During the modeling part, you will master rotation and transfer matrices, Newton-Euler's 6-degree of freedom dynamic equations, state space equations, the gyroscopic effect, and the widely used 4th-order Runge-Kutta integrator. After modeling, you'll thoroughly understand 2 very powerful control techniques, model predictive control and feedback linearization. And not only that, you'll see how they work together hand in hand, forming one global controller that governs the UAV. Finally, you'll have over 2 hours of Python simulation analysis and code explanation. The codes are downloadable as well. Ultimately, I want you to have a bridge between intuition, mathematics, and coding. In this course, the priority is to give you a fundamental understanding of the concepts. If you only memorize stuff, you will forget it quickly. However, if you fundamentally understand it, then it will stay with you for good, and you can modify it to apply this knowledge to other systems too. And that's the true value that you will get from this course. Before you buy, take a look at some of my free preview videos, and if you like what you see, enroll in the course and let's get started. Looking forward to seeing you there. Welcome to the course Applied Control Systems 3 UAV Drone 3D Dynamics and Control. Thank you so much for enrolling. This is the final part in this control system series. While it is recommended that you cover the previous 2 courses first, that teach you about car dynamics, MPC controller, and also MPC constraints, in reality, this is how this UAV course works. Sections 1 to 3, they are independent. It's mainly about deriving a mathematical model for the UAV. It's 3D dynamics, and it's about 50% of the course. You don't need to cover other courses for that. Then sections 4 to 8, for that you should cover the first car course. That is especially important for section 6, in which I'll cover the MPC controller applied to the drone. And so it's assumed that you have already received the basics of MPC in the first car course. And then finally, only section 9 requires you to cover the second car course, in which I cover MPC constraints. That's because in section 9, I apply the MPC constraints to the UAV as well. Just like in the previous courses, this one is also accompanied with a simulation written in Python. The code is explained in section 8, and then in section 9, I add a short explanation about how the MPC constraints were added to the code. The Python installation instructions are in section 8, but you will have additional installation instructions in section 9 because you will have to install additional libraries for the MPC constraints. I've also created some animations for these Python simulations. Knowing how to animate in Python, it's a topic on its own, and it is covered in this course. Python engineering animations bring math and data to life. That course covers everything you need to know about how to create engineering animations in Python. Here are some extra recommendations for this course. It is very important that you follow the material from start to finish without skipping any steps. New knowledge is very often built on older knowledge. And so, if you follow this course in a logical order, then you won't have any problems understanding the concepts that I want to teach you. Also, I tend to give you mini exercises throughout the course. In the end of a video, I might ask you a question or I might give you a small problem to solve, and then you would see the solutions in the next video. I highly recommend you to try solving it first before watching the next video. That way you will understand and solidify the material much better. Finally, if you find that the pace of videos is a bit too slow for you, then just try watching it at 1.25 speed. So that's the plan for this course. Thank you very much. Welcome back. In this lecture, we're going to start looking at a drone from control system's point of view. Let's look at the UAV more closely. This is a typical quadcopter here. It has 4 propellers, or let's call them motors. They are located on the edges of their respective beams. And all of them are at an equal distance from the center. And the distance is here, dm. And the 2 beams themselves are perpendicular to each other. The first thing that we're going to do, we're going to attach an X, Y, and Z body frame to it. This frame is attached to the drone always. It moves with it. It's important to note that this is a body frame, alright, with small X, Y, and Z axis, and not the inertia frame with big X, Y, and Z axis. And the inertia frame is fixed to the ground. So we fix the inertia frame to the ground and we fix the body frame to the drone. And to determine the position of the body frame within the inertia frame, we can have a position vector here that points to the origin of the body frame from the origin of the inertia frame. And we can call it P vector, the position vector. The body frame can translate and rotate within the inertia frame. In fact, that is how we describe the drone's position and orientation in our 3D space. And now, we're going to call the propeller that is on the positive small x side motor 1. On the positive small y side, we have motor 2. Negative small x side, motor 3. And negative small y side, motor 4. Let's now try to identify the inputs and the outputs of the drone using the planned block model. Now, obviously, you need to measure or estimate the UAV's position in the inertia frame, and for that, you need the big X dimension, the big Y dimension, and the big Z dimension, because you have to know the position of the drone in the inertia frame. So you need to know these axes here, the big X, Y, and Z axis. However, there is more to that. You also need to know the orientation of the drone in the inertial frame. You can describe the drone's orientation in the inertia frame using 3 angles: roll, pitch, and yaw, which are phi, theta, and psi respectively. I will treat that extensively in the next section when we learn about 3D rotation matrices. And so these 3 angles are to describe the drone's body frame orientation in the inertial frame. And you can call it body frame orientation in the inertial frame, or angular position in the inertial frame, or the drone's attitude in the inertial frame. So different terminology, but the same meaning. But in addition, we can also measure the drone's angular velocities about its own body frame X, Y, and Z axis. We're going to use the variables P, Q, and R to describe the rotational velocities of the drone about the body frame XYZ axis. Since they are rotational velocities, their units are radians per second. So PQR are radians per second. Okay, but how do we now determine if the rotation is positive or negative? I mean, let's say that your drone is rotating about this small x-axis. Is it rotating, let's say, at 2 radians per second or at minus 2 radians per second? How do you determine that? The convention is to use the right-hand rule to determine if the direction of rotation is positive or negative. If you wrap your right hand around the body x, y, and z axis in the same way like the rotation happens around those axes, and if your thumb points in the positive direction of that axis, so in this case it's in the positive x direction, in the positive y direction, and in the positive z direction, if that's the case, then the rotation is positive. If your thumb, however, points in the opposite direction, then the angles have negative radians and therefore the rotation is negative. So now, for example, if this is your body frame X and now you rotate about the axis like this, then you would grab this axis like this where you can see the knuckles here, and now you see that your thumb points in the opposite direction to the positive x-axis, right? So that means that now your rotation would be negative. So you would say that your P is, let's say, minus 4 radians per second.